Welcome back to part 2 on a series on training a Duelling DQN network to play Breakout with PyTorch. So what we're going to be doing in this video is finishing up the DQN Breakout class. If you remember from the last one, we implemented a class to add some custom functionality to the Atari Gym, and this time around we're going to be filling out the rest of that information. So we'll start down here. I left myself a to-do, decrement lives. So you'll notice in the output when we ran it last, and I'll go ahead and rerun this again, just so we can see what it does. So at this point, it is playing a version of the game Breakout with a completely random agent. So we can see down here that it is displaying, 2 lives, and you can see sort of the lives lost every time. But that's all part of the info library, or the info, it's returning a tuple with that information. So let's also add total reward to this output. So I'm going to print info, and I'm going to print total reward. And I'll show you the problem with the environment as it sits. So if you're training a reinforcement learning algorithm, what it's learning from is the reward, positive or negative. It's trying to maximize the reward value. So the problem we run into here is, even though lives have gone from 3 to 2, the reward is staying at 0. It's not decrementing. We're not doing anything that tells our network that losing a life in the game is bad. So our next step is just to add some of that functionality. We're also going to add some additional processing information, but first off, let's just go ahead and get the decrement lives function in here. So we're going to say in our to-do decrement lives, if, and apologies, I'm looking up the correct dictionary reference over here on the side. You're going to see coding. It can be a little bit messy, even if it's a solution you've built before. So we're going to say current lives equals info and lives. And that should give us, you notice here, we were grabbing info. We're going to grab info lives. So we can go ahead and get rid of that. We don't have to print off everything in info anymore. So we can say, and then we're going to capture the number of lives. So we've already got that. Self.lives equals env ALE lives. So we're starting off with 5. So we can say if current lives less than self.lives, total reward equals total reward minus 1. And this is an arbitrary number. You don't have to do 1. You could do 10, you could do 20, you could do a 0.1. The decision I made during implementation here was that I wanted losing a life to have the same negative impact to the agent that scoring would have a positive impact. So I just went ahead and said total reward equals total reward minus 1 if it's lost a life. And then we're going to go ahead and say self.lives equals current lives. So we're effectively resetting the lives count at that point. We're saying, hey, we're decrementing reward, and we're going to go ahead and mark self.lives as lower. So let's go ahead and make sure that we're getting the values that we think we are. So I'm going to say lives self.lives and total reward. We'll do self dot, actually it's not a self, it's just total reward. And then we'll run the code. So you'll notice lives 5, and we did not, it looks like, so we temporarily decremented total reward here. So we said total reward equals total reward dot 1, but then it did not pass that on, probably because total reward is a variable in step, and lives is a class level variable. So when it finished the step, it temporarily dropped total rewards, but then it brought it back up to 0 because of the variable scope there, which is okay. That's actually what we expect to see. It just looks a little bit weird in the output. So I'm going to go ahead and get rid of this. We no longer need it. And then we can go ahead and code out the rest of this class. So all of this looks like what we want. We're grabbing an observation reward done truncated info. We're adding any reward to total reward. We're updating this. We're appending observation to the buffer. And then if done, we are breaking. So we do need to do a little bit of processing down here. And most of this is to make it a little bit easier to store these things in a replay buffer later. We're going to be turning them to NumPy, or we're going to be turning them to arrays that it can handle later. So I'm going to start off by doing maxFrame equals self.process observation maxFrame. And you might be wondering, where is process observation? We don't have that. You are correct. For now, I'm just going to come down here and say def process observation self, and we're going to just take observation, and for now we're going to return observation. We'll add some here. Even though we're only going to leave it for a minute, I'm going to say we're going to add a to-do here. Add content. So we'll come back and finish that out in a moment. So we're going to go ahead and say under maxFrame process observation, we're going to say maxFrame.to. Nope, not what I wanted, Python. Equals maxFrame.to self.device. So now we're done processing maxFrame. We're going to turn total reward into a torch tensor, a PyTorch tensor. And we're going to say view 1 and -1, and we're going to cast it to a float. And we're really, again, just doing this so that the data is all in a standardized format that we can use a little bit later in processing our batches. And then we can also say total reward equals total reward.to self.device. And if you're not familiar with what I'm doing here, so saying to and a device is sending it to either your CPU or your GPU, depending on what device is. So in this case, I have passed in, I defaulted to CPU, but over here I am saying device equals device, so I'm effectively passing in the GPU information. This is just making sure everything is passed in, it ends up on the same device so that they can all work together. If you're working in PyTorch and you try to, say, pass a tensor that's on the CPU into a model on the GPU, it's going to throw an error. If you try to generate, do multiply two tensors that are on different devices, it's going to throw an error. So this is just making sure that, hey, in this method, when it calls step, it's going to return things that are exclusively back on whatever we've told it the device is. So we're also going to code the done variable. We're going to say done equals torch tensor done dot view -1, and we're going to do the same thing, done dot to, and then really this return information stays about the same. So all of that looks good. As always, we should run our code early and often. So I'm going to go ahead and run main.py and just make sure that that gives us most of what we were expecting. And we can see it does not. But I think that's actually because we haven't finished up the process observation method. Now, you could make a case that we should move some of this logic into process observation. And you might be right, that's not how we're going to do it today, but that would be an option. So in this case, process observation is really an image. So I'm going to name it that just so we get a good feel for what this is doing. I'm going to say img equals image.fromArray observation. So what's actually coming out of this is an array of numbers, which represents the image. This is basically saying, hey, from the PIL image library, that's what we're pulling image in from, we would like to represent an image from this array of observation. And the things, let's talk about what we're doing in process observation here. So, one, we want our network to be able to take images of various types and sizes and then use them in a similar size later on. So, one of the things that we're doing here is standardization. But the big thing we're trying to do is reduce the complexity that the network needs to learn from. So, we're attempting to, we're actually going to take the image and shrink it down to an 84 by 84 size because it doesn't really need to be any bigger. We're also going to be taking the image and rendering it grayscale. And then we're going to be also dividing by 255 just to get everything between 0 and 1 so the model can handle it just a little bit more easily. So let's step through those. So img equals img.resize. And I'm actually going to declare image shape up here because I feel like it does a little bit better as a class variable. You could do that a couple of different ways. I'm going to say self.imageShape equals, and then we're going to be passing in 84 by 84. And again, this is fairly arbitrary. You could do larger or smaller. I chose to make this take 84 by 84 images because that is actually what the paper that we're building off of mentioned. So we're going to say image.resize self.imageShape. Simple enough. We're going to be using, and this is where the PIL library comes in useful. Obviously, it's happily just resizing things for us. That's not something you would get just out of the box in something like a PyTorch tensor. We're also going to just be able to tell it img.convert, and we're going to pass in an L. That's actually going to convert it to grayscale for us. Here, we're going to cast it to a NumPy array. Then we are going to cast it to a PyTorch tensor equals torch.fromNumPy. Now we're going to do something. We're going to unsqueeze the image. So later pieces of the process will require us to pass in a batch size. So instead of having it just as come out as 8484, we actually need to pass it in with a batch size of 1, and so we need something in the batch size column, and we need something in the I believe it's the image channel column. So I'm sure there are more elegant ways to do this, but I'm going to be doing image dot unsqueeze 0, and then I'm actually just going to do it again, and that's going to add 2 dimensions. And then finally we're going to divide everything by 255. So why is it 255? So the color values are between 0 and 255. So by dividing everything by 255, we have just changed it to all values between 0 and 1. And then, like everything else, I'm going to say image equals img.to self.device. And now we're no longer returning observation, we're returning img. All right, so now our process observation code here actually does something. Let's see if our error went away. Hey, and we now have a running, still entirely non-functional, but a running breakout game. So we do have a little bit more functionality to add, but we are almost done with this class, and we are still firmly just getting the wrapper working. This is a fairly long project. There's a lot of code here, but I hope you'll stick with me through it. So the last thing we need to override is the reset function. So when you're working with OpenAI Gym, the 2 functions you're going to use the most are reset and step. So reset has to be done before you use the environment. So you're declaring the environment, you're resetting the environment, and then you're taking steps, taking actions in that environment. So reset is what does that initial setup, and it's where we want to add any changes to the way the environment starts up. So we're going to do reset. Self is all we need to pass in. It takes no arguments. We're going to go ahead and say self.framebuffer equals blank. And you remember we were using that frame buffer up here. So you wouldn't want to start a new iteration with the same environment without clearing the frame buffer. That's what we're doing there. We're going to say observation equals self.env.reset. And if you haven't seen this in Python before, the underscore is genuinely used when you have a variable that you're throwing away. In this case, env.reset, the default one for this environment, returns 2 variables. We only need one of them. We need the observation. We don't need whatever the second one is, so I'm just throwing it in a throwaway variable. We're going to go ahead and reset self.lives to be self.env.ale.lives. And that's the same thing we're doing up here, env lives. So we're just going to reset it to 5. And then we're going to process the observation, just like we did before. And then we're going to return observation. And as always, we're going to go ahead and run the code and make sure everything still works the way it is supposed to. So at this point, we are done with code for this video. We're going to go ahead and throw just a couple more explorations in here, just to walk through some of what we've done. So I think we said that our environment was going to process the observation and set it from what it was before to an 84 by 84 image. Let's see if we can get a state.shape, if it'll give us that, and just confirm some of what we're expecting. So that is what we expected to see. You can see we're getting a torch.size 1, 1. That's the 2 unsqueezes we added. And then we're also getting our 84 by 84, so that's what I expected to see there. And that is probably most of what we wanted to validate today. So I'm going to go ahead and stop this video here. In the next video, we will go ahead and start coding up the model. And then we've got a few more classes to do before we get to something where we can actually start training. So I'll see you in the next video.